What were they? Fission and fusion. Does anybody remember what fission is? Oh, you just can't see it. Red. Does anybody remember what fission is? A large nucleus gets hit with a neutron and breaks it apart into a small plus a small plus more neutrons, correct? I need a color that you can actually see. There we go. Okay, does anybody remember what fusion is? It's the exact opposite, so we get a small plus a small, giving us not really a big, but helium, plus lots and lots and lots and lots and lots of energy. What does fusion? In our universe, what does fusion? The sun. Does anybody remember why fusion is great? Because it doesn't require very much to start the reaction. Think about how tiny a hydrogen is compared to uranium. Hydrogen has a mass of 1, uranium has a mass of 238. So you need a lot less reactants than you do in fission. All right, so now that we kind of are on the same page with what fission and fusion are, we're going to talk about the applications of them. So what do we do fission for? What is the point? So basically nuclear energy. All right, so we're going to spend a lot of time talking about nuclear reactors. When I'm talking about nuclear reactors, I'm talking about power plants for the most part, nuclear power plants. Okay, in nuclear power plants, they are using controlled fission. And when you use controlled fission, you have a steady release of energy. And the conditions are very similar to what we needed for an atom bomb. We talked about atom bomb a little bit last week, right? All right, so here are the 5 things you need in a fission reaction. You need a fissionable fuel, which we talked about it being uranium and plutonium, right? We need a moderator. Does anybody remember what a moderator is? It slows down the reaction by absorbing neutrons, right? It kind of like steals them so that they can't react with uranium. We need some sort of control system to kind of control the reaction. If it's going too fast, we can slow it down. If it's going too slow, we can speed it up. We need some sort of way to control it. We need some sort of way to remove the heat because these reactions release a lot of energy. If it keeps getting hotter and hotter and hotter, it makes the reaction go faster and faster and faster, kind of like a chain reaction. And then last but not least, we need some sort of radiation shield because nobody wants to be exposed to radiation. So let's talk about each one of these individually. So the first one is fissionable fuel. And we talked about this a lot on Tuesday. We have uranium-235 or plutonium-239. And remember, those mass numbers are talking about a specific isotope. Okay? Uranium is usually found as uranium-238. That's what's on the periodic table. So the majority of uranium is 238. So the kind that we use in fission is not the average, correct? It's the one that's found in a small percentage. Okay, this is exactly the same type of fuel we use in atom bombs, but instead of having to have a supercritical mass. Does everybody remember what a supercritical mass was from Tuesday? Anyone? It's that point in which your product is being made faster than the reactants are reacting. So it's almost like the process is going faster and faster and faster and faster and faster, as opposed to if it was just critical, it was kind of happening at the same speed, and then there was subcritical where neutrons are being stolen, so it was actually like slowing down the reaction. This is where there's neutrons in excess, so the reaction's happening very quickly. But since we don't need a supercritical mass, the purity of the fuel is not as important. Okay? In order to make an atom bomb, we had to have pretty pure fuel. We had to find a way to separate the different types of uranium in order to get the bomb to work properly. And these types, since we don't need a big giant explosion, we don't need a super pure fuel. Okay, most nuclear reactors can use natural uranium. Natural uranium is uranium that's found in our soil. And again, it is, for the most part, uranium-238. And only 0.7% of our uranium contains uranium-235. So think about if you have a gram, 0.07 grams is what is actually doing the fission. Okay. All right, U.S. reactors, which the reactors that we use around here, every country has different regulations, but for ours, we used enriched uranium, which means we have found a way to increase the percentage of uranium-235 to approximately 3%. And again, enriched means that it is above what is naturally found in nature. The uranium found in nature is less than 1% uranium-235. What we need for our reactors is 3%. So there are different ways, and we're going to talk about how to do that in just a second. All right, so let's spend a little bit more time talking about the fuel. Uranium is a mineral that is mined. It's mined like coal. You dig a hole in the ground, you dig it out, you bring it up to the surface, you find a way to isolate it. We find it in the ground as uranium octoxide, which is 3 uraniums for every 8 oxygens. For the most part, we can find uranium in Canada, Australia, and Russia. They have big supplies of uranium. But we can find it in the United States, and we produce 4% of the world's uranium from Nebraska, Wyoming, and Texas. Once mined, it is milled. Just like most things when you mine them, when they come onto the ground, they're not in the form you need them to be in, correct? So you have to do a little bit of work to make them what you want. So once we pull up uranium octoxide, we convert it into uranium hexafluoride. So we're breaking the bond between uranium and oxygen. We are bonding it with fluorine, and then we enrich it. Does anybody remember what enriching means again? Talked about it a slide ago. It's above what's found in nature. So it is a higher percentage of the isotope we want. Okay. However, there's uranium-235 and there's uranium-238. We want 235. We have 238. That creates a problem. So now, when we're trying to enrich it, we have to come up with some sort of way to separate these guys. We want uranium-235. Well, isotopes are 100% identical in every way, shape, and form except for the number of neutrons. Their protons are the same. Their electrons are the same. And if you remember when we talked about bonding, the electrons is what affects how things bond. So if uranium-235 and uranium-238 have the exact same electron structure, they're going to bond in the exact same way. So we can't use chemical reactions to enrich it. We have to come up with some other way. So we have to use physical differences. Uranium-235 is lighter than uranium-238 because it has 3 less neutrons, right? Is it a big difference in weight? No, but it's a difference nonetheless. It's the only thing we have to go off of, so we have to find some sort of way to make that difference work. And so we actually have 2 different ways that we do this. We have gaseous diffusion. So you guys ever been taught the definition of diffusion when you've talked about gases or anything? Diffusion is just when something spreads out. So if somebody is in the back corner of the classroom and sprays perfume, eventually you're going to smell it at the front of the room, right? Because it is diffusing, correct? Okay, so if we're talking about gas diffusion, we are talking about gases diffusing into a different room or into an area, so on and so forth. Specifically, I like to compare this to a helium balloon. If you fill up a balloon with helium and you leave it tied to a chair or something overnight, in the morning when you wake up, what happened to the balloon? It starts to sink. If you leave it sitting for long enough, doesn't the balloon actually start to get smaller? Does that mean there's a hole in your balloon? No. What happens is every membrane, which is kind of what that is, it's called a semi-permeable membrane, and it has holes in it. Okay, things can escape through the holes if you let them sit, if you leave it sitting there long enough. So what ends up happening is the helium starts to go out of those little tiny holes because helium is very, very, very small compared to oxygen, right? Helium has a mass of 4, oxygen has a mass of 16. Okay? So since it's so much smaller, it can kind of seep through these little holes. That's exactly what happens in a gaseous diffusion is uranium-235 is technically just a tad bit smaller than uranium-238. So if you put it in a semi-permeable membrane, it should escape through the holes before uranium-238. But since they're so close in, it's not a perfect science. Okay, but we do what we can do. So what they do is they put it in a chamber, they let it diffuse. And then whatever gas they collect, they put in another chamber, they let it diffuse. And they keep doing this until they get to the percentage they want. So it takes a long time. Well, we don't have forever and a day to do this, so they had to come up with another way, and so they used something called gas centrifugation. And a centrifuge is basically something you put, the one I have for our lab, you put test tubes in it, you stopper a test tube, you put it in, there's like little holes that are test tube size in a circle, and then you turn it on and it spins really, 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 really fast. And what happens is all of the heavy molecules get flung to the bottom of the test tube, and the lighter molecules stay kind of surfaced at the top. Those of you who are in nursing school or whatever, this is how they test blood a lot of times. This is how they see what type of blood you have and all that. I'm not a nurse, so I don't know. I just know that they do it with blood a lot. But it creates a force that is 1,000,000 times that of gravity, which causes the heavier molecules to fly to the bottom, so the uranium-238, and what's left at the top is uranium-235. So this is a much quicker process, and they don't have to repeat it over and over and over again. And again, this is how we enrich our uranium fuel. We're trying to get more uranium-235, less uranium-238. Right, so once our uranium is enriched to the desired degree, it is then converted to uranium dioxide. So you're 1 uranium, 2 oxygens. And this is a ceramic material. What's ceramic mean? Okay, everyone knows what ceramics are, correct? Ceramics, don't we put them in a kiln? Don't they get heated up really, really, really high? Does it cause them to break or anything? No, they can withstand high temperatures, okay? What they do is then they are made into pellets that are 1 centimeter by 2 centimeters high. And then they stack them on top of each other, and then they encase them in a steel rod. So basically, they are trying to make a uranium rod that has some sort of metal protection on the outside of it. Okay. When you are making a nuclear reactor, you take 40 to 50,000 of these rods to make something called the core. This is where all of the fission is going to be taking place to create our energy. All right, so we've been talking about uranium. Let's talk about plutonium a little bit because it does fission as well. It actually does fission a little bit better than uranium does. Plutonium is a fissionable fuel. However, plutonium is often used in bomb production. So therefore, if we were mining and we were creating a whole bunch of plutonium, it would be bad if we had a terrorist attack. It would be bad if somebody was able to somehow smuggle it out of the country. It would be bad if it got into the hands of the wrong person because then they could make bombs with it. Okay, we don't want other people to be making nuclear bombs, correct? That would be bad. So in interest of keeping that from happening, we prefer to use uranium because if uranium would wind up in the wrong hands, it's usually not in a very pure form. Like I said, it's only 0.7% fissionable, which is a very small percentage. So yes, could people make a bomb? Yes. But most terrorists or whatever don't have the material needed to enrich it. So what bomb they could make in the grand scheme of things would not be a very powerful one, so it wouldn't cause much damage. So it's a much lesser evil as opposed to plutonium. It was actually banned in 1977 in the United States. So we're not allowed to use it. Okay, so now let's talk about our moderators. This is the material that slows down the neutrons so that it can be captured by uranium. So if you think about how tiny a neutron is, it has very, very small mass. It has no charge, so it's not going to be attracted to positive or negative charges. There's nothing stopping it. It'd be like somebody shooting a bullet at you and there's no air resistance. When it comes into contact with you, it just kind of passes right through. It doesn't even get slowed down by the friction. Okay? It's really, really hard for the uranium to kind of reach out and grab it. So we need some sort of material that can kind of slow them down. So we used, the more enriched our fuel is, so the higher percentage we have of uranium-235, the less important the moderator is, because the more fissionable product we have, the better they are at grabbing neutrons. But if we don't have very much uranium-235, we need the neutrons to be nice and slow so the few that we have can concentrate. So honestly, in the United States, we use heavy water as our moderator. And what heavy water is still H2O, correct? 2 hydrogens, 1 oxygen. But usually, water is the most common version of hydrogen, which is hydrogen 1, which has 1 proton, 1 electron, and that's it. Okay? Well, as a moderator, we need it to be a little bit differently. We need it to be heavier. And the reason they call it heavy water is because instead of using hydrogen 1, they're going to use hydrogen 2. The only difference between hydrogen 1 and hydrogen 2 is a neutron. So it's written, instead of saying H2O, because that's how we usually say water, well, if we had to type out heavy water every single time, it would get a little bit cumbersome. So they came up with a new substitute for it, and they like to call it D2O. D stands for deuterium, which is the actual name for hydrogen 2. So heavy water contains hydrogen 2 instead of hydrogen. Another moderator that can be used is graphite. We don't use it in the United States, but there are several power plants in Europe that use graphite.
And Russia.
And Russia.
Or Russian. Whatever. Russian.
The Russians aren't a great example of
Some European
perfection
Russian.
in the nuclear power department. Okay, so let's talk about a control system now. Because remember, this is a chain reaction. Once you start a nuclear reaction, there is no way to stop it. All you can do is slow it down and hope that they run out of neutrons and the reaction can no longer take place. So we need to have something that can slow down and speed up a reaction. So when remember, we have our core. We have our fuel rods in there. We have our uranium cased in stainless steel. And they are inserted into the heavy water. The heavy water has neutrons. It's throwing neutrons at the uranium. Well, it's nighttime, and it's daytime, and we don't need as much electricity. So they need a way to slow it down. Well, you can't make the reaction stop. So what they do is they have control rods, usually made out of cadmium or boron. These are kind of like poison for nuclear reactions. What they do is they steal all the neutrons. So they will then lower these control rods into the reaction, into where the fuel rods are and the heavy water. They'll lower these control rods down in there, and they basically steal all the neutrons. So if there's no neutrons, can fission take place? No. So the reaction is slowing down, but stopping it is not quite the right word, correct? Okay, the more that you insert, the slower the reaction. The more you take out, the faster the reaction. So instead of, we're used to, if you need more energy, you add more fuel, correct? If you need less energy, you have less fuel. Well, in this case, we have to do it kind of the opposite way. We have to add more control, take away more control. Okay, but so far, none of this sounds very dangerous, right? We have heavy water, we have the rods, we have 2 different types of rods. So far, what is making this go exploding? Why is this bad, right? Well, we need to talk about heat. Fission produces a lot of heat. That is what makes it important. That is what makes it a good generator of power, is because it produces so much heat. So we need some way to remove the heat, because it's when the process heats up, it makes fission happen faster, which produces more heat, which makes fission happen faster, producing more heat. The hotter it is, the more efficient the process. So we need some way to control the amount of heat to keep the fission reaction kind of under wraps. So in order to do this, they pump a fluid through the core of the reactor. Now, when you say fluid, usually we're thinking about liquids. And it isn't necessarily a liquid, because gases also move like a fluid. You can move air molecules about as easily as you can move gas or liquid molecules. So a couple that can be used, they're not necessarily used, is air. You can just use the atmosphere, but that's not a great heat removal system. Helium's a pretty good one. Carbon dioxide's a really good one, because they have such low temperatures, such low melting points and everything, that it's really, they're a very cold gas. And for the most part, when we're talking about heat removal systems, we use water. Okay, why? Because water is found in such excess that it's cheap, it's accessible, it's easy to get, it's easy to control. There's lots and lots and lots of it. So for the most part, we use water. Some places actually use heavy water as well because then your heat removal system and your moderator is the same thing. So it's kind of like one less ingredient that you have to keep track of. And then some also use liquid sodium because, again, of its such low melting point, because sodium's usually in solid at room temperature, right? Because it has such a low melting point, it's very cold in the liquid state. All right, and last but not least, we need to talk about the radiation shield, probably the most important part. Most nuclear reactors use a double barrier to protect workers and people who live nearby. Nobody wants to be exposed to radiation. We don't want radiation getting released into the environment. This is what causes dangerous health effects, correct? So, they do two things. The core of the reactor is encased in a steel container. There's very few things that can permeate steel just naturally. Okay, gases don't go in and out of steel. Liquids don't usually go in and out of steel, so it's a pretty good barrier. But radiation can still go in and out of steel. So the steel is there to keep everything from keeping things from getting to the core. But things can still get out of the core. So then they need to add a concrete dome. And if you guys remember when I was talking about alpha, beta, and gamma particles, we needed 6 feet of lead and concrete to contain gamma. So they have it encased in a steel container, and then they add 6 feet of concrete to allow all the radiation to stay in the core. Because again, we don't want people getting exposed to it. Some countries bury it in the ground. We don't. We encase it in concrete because that's not a perfect science, because we have earthquakes, we have fault lines, we have places in the ground where there are lines, vent lines. Okay, so then that could release radiation. Some countries do it, but we don't. All right, well, there are several different types of reactors. There are research reactors, and these are actually really small reactors, and they just sit in a tank of water. The water can then act as a moderator, a coolant, and a radiation shield. If you're not producing very much radiation, the water is going to contain all the radiation, keep it from seeping out. These are actually used for experiments. So one experiment that was explained in your book was a neutron activation analysis. This is used to determine what elements of an unknown is made up out of. So, of course, and I can't think of an example off the top of my head right now. Nope, I can't come up with an example off the top of my head right now. Sorry. So let's just move on. Let's talk about production reactors. These are the ones we really care about. The production of energy. The neutrons generated in a reactor can be used to make other isotopes not available in nature, but with useful applications. So production reactors, honestly, this is how we get our radiation therapies for health, cancers, so on and so forth. This is how we get our chemotherapies. We are going through a nuclear process to create these radioactive isotopes. These radioactive isotopes are then used to help people figure out what's going on in their bodies, because we can detect radiation where we can't detect just normal isotopes. All right, and then we're going to spend a lot of time talking about electricity. Okay. The U.S. has 104 reactors, nuclear reactors, and this produces 19% of our electricity. 42% of it comes from coal, 25% of it comes from natural gas, 8% of it comes from hydroelectric, which is water, 5% comes from solar, wind, and geothermal, and 1% comes from petroleum. The world as a whole has over 400 reactors. So us as a country have about approximately 25% of the reactors in the whole world, which is a pretty good percentage. Does everybody know how a normal electric power plant works? Does everybody know how a coal power plant works? So let's just talk about a coal power plant. What do coal power plants burn, obviously? Coal. So basically what happens is, and I'm going to attempt to draw a nice pretty picture here. We have a turbine, and I'm going to explain what all these are in a second. But we have a turbine, and it's kind of like a coil, and we need to burn something. Okay, so we use coal around here. We have coal power plants. We burn the coal. The coal heats up the water that's in kind of like in a giant tank. The water then gets heated up. It then produces steam. The steam comes up and it turns the turbine. Turbines can be made out of lots of different things. The turbines then turn a generator. In the process, it's no longer over the fire anymore. The water cools back down. It recondenses. It gets pumped back into here. It's heated up. It produces steam. It turns the turbine, which then turns the generator, gets cooled down, comes back over, gets heated up, produces steam. This is how power plants work. All power plants, for the most part, do the exact same process. The only thing that's different is how do you heat up the water. Okay, we use coal. You could use hydroelectric, where you're using the movement of water, and that just turns the turbine itself. You can use solar energy. That's not as efficient. Why isn't solar energy as efficient? Does the sun shine all the time? No. Okay. All right, so how does electricity work? Electricity is basically the movement of electrons. Okay, that's why metals are good conductors of electricity, because they have free electrons that can move a lot easier than nonmetals. So there's actually two different types of currents. We have a direct current, and these are what we see in batteries. Batteries push electrons out one end and they suck them into the other. And it's just kind of like a continuous circuit. Over time, the circuit becomes corroded or whatnot, and it slows the process down, and that's when your batteries go bad. You throw them out, you put new ones in. Okay? Alternating current, this is what we think of when we think of electricity in our house. This is a coil of wire, and it is rotated in a magnetic field, causing the electrons to move back and forth. And when I say move back and forth, I'm talking about 60 times per minute. So they're moving back and forth 60 times in 1 minute. That's pretty fast. This is what we think about when we're thinking about our homes and our businesses. This is the type of electricity that we're using. So, how do we rotate the coil? Because 60 cycles per minute is pretty fast. How in the world are we going to maintain that for a very long period of time? Well, there are several ways. Moving water, that's why we have dams. A lot of times dams are created to, 1, create a lake, 2, create electricity. As the water flows through the dam, it runs over paddles. It turns the paddles turn the turbine, creating electricity. We have electricity for our houses. Another thing is a windmill. The wind blows the paddles on the windmill turns the turbine. Today would be a good day because it's really windy outside. We burn natural gas or coal. It boils the water. The steam then causes the turbine to turn. And then, instead of using coal, we could actually use the heat of fusion to boil the water to turn the turbine. But do you guys see how it doesn't matter what the source of energy is. We're trying to turn a turbine to create the movement of electrons, and that's what creates the electricity. Okay, so here was the picture I was trying to draw a second ago, and that's a much better way, isn't it? So basically what we have is over here in we have water right here. Yeah, I knew that would happen. We have water in this. It's being heated up. As it gets heated up, it produces steam. The steam comes over here. It turns the turbine, which in place turns the electric generator, and then it condenses. Well, we need this process to happen a little bit faster because it's going to take the steam a long time to cool down and recondense. So oftentimes they have an additional water source that comes in from a surrounding lake or a surrounding river of some sort. They pump it in as cold. It comes over here. It cools down the water at the same time, though it's heated up, correct? So when it goes back out into the water source, it's probably a little bit warmer than when it started. As it condenses, it comes back down here. It gets pumped back into the reactor where it's heated back up. Okay, this is a boiling water reactor. Okay, so now we've talked about it for coal, so now let's talk about it for fission. Same exact thing. Right here is where we have our fuel rods and our control rods. Instead of it being coal burning, we are putting, this is probably heavy water, not just water itself. It's probably heavy water, which means it's neutron rich. So all you have to do is supply the control rods and the fuel rods. The fuel rods come into contact with the neutron, create fission. The fission releases a lot of energy, heating the water, making the steam. Same exact process. Instead of using coal, we are using uranium. That's one type. The United States uses both types. They use this type, and they also use something called a pressurized water reactor. Same basic concept, just a little tiny bit different. The only difference here is because the pressurized water reactor has 2 water loops because they are trying to contain the radiation just a little bit better. So if you notice right here, we have our concrete shield containing all the radiation. Here are our control rods and our fuel rods. Here, the red is showing you the heavy water. The blue is showing you just normal water. And then over here we have our condensed cooling water. So it's almost like they have 3 separate parts of water. We have the heavy water, red. We have the water that's actually being produced as steam, is the blue. And then over on the right side, this area is water coming in from a lake or river, so on and so forth. Basically, the way this is different is we use pressurized water. When you increase the pressure, it prevents things from going into a gas phase. So yes, the red water is the heavy water. Yes, it is being heated up. But since it's under such high pressure, it doesn't actually form steam. Okay, it allows us to have more control. If that water, which again is being exposed to radiation, were to get released, it'd be bad. It's a whole lot easier to contain liquid water than it is to contain steam. So we don't want the radiation leaking out, so this is kind of supplying an extra control piece to it. If we keep all of that water in our containment lead and concrete, then the less chances of it getting escaped. So instead, what it does is the pressurized water, again, is not forming steam. It heats up and heats up and heats up. So then as it heats up, it moves to the right and it comes into our steam generator. Here's just normal water. Okay? Normal water, it's not under pressure, so when it's heated up, it's going to produce steam, right? As it produces steam, it comes up, turns a turbine, turns a generator, and then we try to get it to condense. How do we get it to condense? We need colder water from an area. It's getting pumped in and out and in and out. So basically, we just have 3 loops of water that are continuously moving. Okay, these are what the United States use, but there's actually several different types of reactors. Canada uses the Canadian heavy water. This is very similar to the pressurized water reactor I was just telling you about, except they don't use enriched uranium. They just use the natural stuff coming straight out of the ground. So in order for this reaction to take place, they need a better moderator. Okay. So they use heavy water as well. Another type of reactor is the high temperature gas cooled. Okay, this is actually much more efficient. However, it's also more expensive. Usually when you increase the efficiency of a machine, it usually also includes an increased price tag. It also produces less waste, and it can withstand loss of coolant accidents better. So basically, with this type of reactor, if something were to happen and our water was released or our pumps that were pumping the water stopped, this reaction could maintain itself until we could fix the problem, unlike the power plants I was just telling you about. If we lose coolant in the power plants I was just telling you about, the reaction speeds up until it causes a radiation leak. Okay, these type of power plants can withstand a little bit better. Why? Because they use graphite as a moderator. We use heavy water. These types use graphite. Graphite not only is it a moderator, but it also absorbs lots and lots of heat. So it's not only is it kind of competing for the neutrons, but it's also absorbing heat. Okay, another type is liquid metal fast breeder. This produces more fuel than it technically uses. It also converts uranium-238 to plutonium-239. That's what I mean when I say it produces more fuel than it creates. In the process that it does fission, it creates a new product that can fission. So when uranium-238 is broken down, it produces more fuel. So it's like if you could somehow go to the store and buy gas that just kind of regenerated more gas and more gas and more gas. That'd be kind of nice, and you wouldn't have to refill your car ever. Wouldn't that save you lots of money? So our fuel is creating more fuel. If only that was possible. In this type of reactor, they use liquid sodium as the coolant because it's less corrosive, which means that there's less of a chance of the coolant leaking out, which is what we want. This is a very efficient reactor, so we don't want the coolant going anywhere. Breeder do what? Why don't we have those? Because breeder reactors have bad luck. These reactions are very, very efficient. So when things go wrong, they really, really go wrong. So we've had a couple of these. We had one in Idaho, and this one overheated. Something happened with the coolant. It overheated and melted half of its core. When the core melts, you have to think about how high the temperatures must be. And so if the core starts to melt, the chances of it melting through the steel chamber and through the concrete increase as well, which means radiation leaking. Okay. We also built another one in Detroit, and this overheated due to the coolant line being blocked. Same thing happened. The core started to melt, then it melts through the steel chamber, then it starts to melt through the concrete. Chance of it leaking into the atmosphere. So these are a lot harder to control because they're so efficient. So these reactors sound great, don't they? Yay. We can use a fuel, produce a fuel, win-win situation. Well, they also produce plutonium, which, if you remember, was banned in 1977, right? Why don't we want to be using plutonium? Why don't we want to be creating plutonium? Because if it were to get in the wrong hands, it's a very, very powerful nuclear weapon, isn't it?
What's the difference between plutonium and weapons-grade plutonium? You always hear on the news where they're talking about like weapons of mass destruction and weapons-grade.
I honestly don't know. I'm assuming that weapons-grade plutonium has been enriched. Just like we enrich uranium to make it react better, I'm assuming the same thing. Plutonium, probably the first isotope of plutonium probably isn't as reactive. If we could probably enrich it the same ways and make it react a little bit better. Okay. Another bad thing about breeder reactors is sodium. Sodium is an alkali metal. He's in that first column. When we talked about the periodic table, didn't I tell you that first column is very, very reactive? It likes to react with water. Isn't water around us all the time? So sodium, yes, is a good coolant. However, it is very reactive with water, which usually reactors contain water. And if it is exposed to the air, it could very possibly burn in air. So if it were to have a leak, it would be very, very bad. Okay, because we have water in our atmosphere. If it were to leak, it would just go boom. Also, if there was a coolant leak, it could speed up the fission reactions, possibly causing a nuclear explosion. Because plutonium is so reactive, if this is the fuel that we're creating in this type of reaction, we're basically creating an atom bomb. Aren't we? Breaking down uranium, we're basically creating an atom bomb. And that's kind of hard to control. Okay, the reason breeder reactions are a little bit different than the reactors we've been talking about is because in our type of reactors, we use heavy water as both the moderator and the coolant. So if we were to lose the coolant, we would also be losing the moderator. So not only would we not be cooling our system, but we would be losing the neutrons. So the reaction would start to slow down on its own. In these type of reactions, neutrons are being created in the reaction itself, so we don't honestly need the moderator once the reaction has started. So it would just keep getting hotter and hotter and hotter and hotter. Okay, so why is all this important? Why in the world do we want to use nuclear power plants if there's all of these dangers? Well, cost, to be quite frankly. Coal power plants are really, really cheap to build. However, it costs a ton to operate them because you need so much fuel in order to maintain the amount of electricity that towns and cities need.
Wouldn't it be like cheaper in the long run
To do what?
to get the
Nuclear?
no this last one? What were we talking
The
about?
breeder reactors?
Yeah.
Yes, if we could figure out how to control them a little bit better. Yes, but we're just safety in the United States. We don't want to cross that bridge and become Russia, where they've had lots and lots and lots of accidents. Nuclear power plants, on the other hand, are very, very expensive to build. Why are they so expensive to build? Because there has to be so many safety precautions. If something happens at a coal power plant, if we get an earthquake or we get a tornado or somehow we get hit by a tsunami in Missouri, I don't know how that would happen. But if we had some of these basically, the coal would no longer be burnt, which would make the reaction stop right then, right? But the bad thing about a nuclear power plant is if once the reaction starts, there's nothing to stop it. So if we have these external events that we have no control over, it could possibly make the reaction go even faster, which could then cause an even bigger problem. So they're very expensive to build because you have to build in all of these safety protocols. But at the same time, the amount of fuel you'll need is so small. I think I remember I looked it up one time, but I believe it was 5 grams of uranium, which is about the size of a paperclip, would power the city of Springfield for 6 months. So it would cost a lot to build a power plant, but the amount of fuel you need is very minuscule. So I feel like in the end, maybe nuclear power plants would end up being cheaper. But who knows? Okay, so the reason nuclear power plants kind of have a bad rap is because of equipment failures. What?
It says it's basically impossible for the stuff to explode that we use today. How?
The
If they're not the best ones.
which one? Uranium?
No, like the power plants that we use
Yeah.
now.
We're going to talk about it in just a second. But basically, give me 2 more slides, and then we'll talk about it. Okay. All right, so we need to talk about equipment failures a little bit. Nuclear reactors, or at least the types in the United States, cannot explode like an atom bomb. When people think about nuclear power plants, they think of all the bad examples that we've had. But usually the really, really bad examples usually are using plutonium and not uranium. That's why our power plants use uranium, because they are not going to explode like an atom bomb. If the containment building is compromised, then yes, you will have a release of radioactive material. What causes nuclear reactors to have equipment failure is something usually has to happen in the cooling system. Okay, the cooling system has to be disabled somehow. So, for instance, one thing that could happen is in a fission reaction, you're creating really, really, really high temperatures. Okay, high temperatures could then lead to decomposition of water. We just talked about decomposition reactions. What happens in a decomposition reaction? It breaks one thing into 2. So if we're breaking apart water, we're going to get hydrogen and oxygen. So if we decompose water, we're going to get hydrogen. Hydrogen is an extremely flammable gas, so all it would take is a tiny little spark to ignite the hydrogen. If we ignited the hydrogen, it would cause a chemical explosion, which would probably affect the concrete that we have built to contain the radiation, therefore releasing the radiation. Okay, the reason that our types of reactors do not create atom bombs is because they're honestly not a chemical reaction. Usually when radiation is being released, it's because of a steam reaction. Okay? Other types of reactors that we don't use in the United States sometimes will have a chemical reaction. But our types, just the way that we control it, the way that we have it, uranium is not going to produce an atom bomb. That's plutonium. So since we use uranium, the most we're going to have is a steam explosion, which yes is bad. And yes, it releases radiation, but it is not going to blow up like a bomb. We're not going to have the mushroom cloud. Okay? Why? Because we're using a different source. And the source does not do fission as completely as plutonium. Okay? A different cause that could happen to have equipment failure is if the fuel gets hot enough to melt. Okay, so if our fuel rods start to melt, it could melt through the concrete floor, and then it could release the radiation down through the ground and into like our groundwater, and then that could spread really easily to everybody because everybody drinks water. We need water for everything. Okay, another bad thing about our power plants, our reactors that we use, is we need that water. Like I keep saying, we bring it in from a river or a stream nearby. We use it to cool, but as it gets released back into it, usually it's just a little bit warmer. Okay, well, 1 degree in that type of natural habitat is bad. It doesn't sound like it's a lot, but 1 degree changes the amount of oxygen that is dissolved in the water. If there's less oxygen in the water, fish can't survive. And if there's less oxygen in the water, then there's probably more plant life. So it's like the fish start to die off and the plants kind of start to take off. So it's kind of, that's when you get unhealthy streams. All right, but the big problem with our reactors is radioactive waste. Okay, each reactor contains 50 to 100 tons of fuel, and it can create 2 cubic meters of waste per year. But if you think about 2 cubic meters in one whole year, that's really not a lot of waste compared to how much waste we must produce when we're doing coal power plants, right? 2 cubic meters in an entire year is not that much waste. It's bad because it's radioactive waste, so what in the world are we going to do with it? Like last week when I talked about we can't find a lead box and stick it in the corner and tell nobody to mess with it for 1,000 years. We have to come up with some way to maintain it. So what do? Do we reprocess it? Well, when we reprocess our uranium, we produce plutonium, which we already discussed is a bad idea. So the government said, nope, we're not going to do that because we don't want to create plutonium because plutonium is bad. So we got to come up with another plan. So we need to figure out some way to store it until its half-life has occurred and it is no longer radioactive, which again can be days to millions of years, correct? So there were 3 sites. There was one in Washington, one in Texas, and one in Nevada that the government thought would be good sites. And they thought they would be good sites because they were relatively stable climate-wise. They didn't have a lot of fluctuations. They didn't occur when in places where there was a lot of natural disasters. They had a pretty normal fluctuation in like moisture. It didn't rain a lot, but it wasn't really hot. It was nice and even. They want these type of storage spaces needs to have constant temperatures and constant humidity levels. Well, our government system works on politics, right? Well, at the time this was being discussed, there was a Texan pretty high up in the government chain, so he said, no, I don't want it in Texas. And there was somebody from Washington pretty high up in the government chain, so he said, no, I don't want it in Washington. So it was decided that it was going to be in Nevada. So they chose a granite mountain in Nevada, and it was chosen because, again, it was in a very dry area with little rainfall, and the water table is very low. So therefore, even if it were to be released into the ground, it wouldn't contaminate the groundwater because the water table is so low. Okay, what they do is they drilled tunnels into the mountain, and they kind of like truck the waste in there, and the mountain acts as a containment shelter. We don't need to add all the concrete. We don't need to add all of these things because the mountain itself is made out of granite, which is basically doing that for us. Okay, well, funding for this site was canceled after they put $12 million into it 8 years later because, anyone want to take a guess?
It leaked.
The power shifted in the government, and now the Nevada person that was in charge of the Senate, leader of the Senate, was now from Nevada, and he said, I don't want it in Nevada. So then after spending $12 million, they said, nope, so now it's just kind of sitting there. Nobody can decide what to do with these things. So another thing that I always kind of like to talk about right here is radioactive wastes are pretty common. They're around us all the time, especially around here because around here we have a lot of basements and crawl spaces in our houses, correct? Well, radon is a very radioactive element, and it builds up in basements. It builds up below ground level. So any part of your house that is below ground level can have a buildup of radon, especially if it's an older house and possibly has foundation cracks or something like that. And the reason that it builds up is because radon, again, has a mass of 222, which is much heavier than most of our gas molecules in our air, like oxygen and carbon dioxide. And since it's so much heavier, it just sinks. So if you live in a basement that doesn't get very good circulation, that stuff's just going to build up over and over and over time, and that can lead to lung cancer.
It's scary.
Yes. So if you have a basement and you live in an older house, you might want to get it tested for radon levels. It's not a huge problem around here, but it's a problem nonetheless. Okay, so if we're not allowed to store it in the granite mountain in Nevada, nobody can decide where to store it. The government can't make a decision. What in the world are we supposed to do with it? Because we already talked about the fact that we have 104 reactors in the United States, correct? Who are producing 2 cubic meters of waste every single year. So what are we going to do with it? Well, for now, we store these fuel rods that are spent. They call them spent fuel rods, which means most of the fuel has reacted into other radioactive isotopes. We store them in giant swimming pools at the reactor site.
That's safe.
The water, like I've said before, it kind of acts as a containment of the radiation. It keeps the radiation from releasing. Water regulates temperature. It's hard to raise and lower the temperature of a water very quickly, right? And so it just kind of keeps these nice and underway. So is this a permanent solution? No, but we needed somewhere to put the radioactive waste. The government wasn't making a decision, so the power plants themselves had to kind of come up with something. So they all have giant swimming pools, and they store radioactive waste there.
What happens when it fills up?
We're not there
They
yet.
don't know that.
We don't know
They
yet.
build a new one. What do they do with the old one? Just cover it up?
Until we decide what we're going to do with these wastes, we're just...
That's retarded. I hate the government.
Well, what happens when our landfills get full?
Ship it to outer space.
on.
Okay, so... But when people think about nuclear power plants, the first thing that pops into your mind is all of the accidents that have happened, correct? And we've had several major accidents. The first one was in the Soviet Union. Shocker. Okay, I'm not even going to take a stab as to how to say that name. But this occurred in 1957. So this is when nuclear power plants were relatively new. The science was new and we weren't really sure how it worked. But this is by far one of the worst accidents to affect a military plant, and this occurred in the Soviet Union. Okay, in this process, they were producing plutonium. And they didn't know what to do with the waste, just like we. We don't have a good solution for how to put the waste, so what they did is they went, let's just dump it into local rivers and lakes. That's a good place for it because, hey, water is a good a shield for radiation, right? So let's just dump it in some water. Okay? But on September 29th, that's not even the big part. That's just what they were doing. That's not even the accident. But on September 29th, the cooling system on a waste tank failed, causing it to overheat, leading then to a chemical explosion because plutonium creates atom bombs, correct? Not uranium. This is why we don't use plutonium, because plutonium goes boom. We use uranium because at the very least, at the very worst, we're going to have a steam explosion, which is better than an atom bomb explosion, correct? Okay, this spread radioactive fallout over 375 square miles. But what made this accident so bad is that they tried to cover it up. This occurred in 1957, and they kept it secret until 1977. And they actually didn't publicly admit that it happened until 1989.
How could they keep something like that a secret? Yeah, right?
The government. Even the Russian government.
Well,
Oh, it makes me want to pull my hair out.
in your textbook, it does say that the CIA knew about it,
Yeah.
but not
CIA.
like officially. I'm sure we found out that information through our back channels somehow, but I don't think we officially knew. Does that make sense?
Ooh.
Okay, but guess what? We had a bad one too. We had one in 1979 called the 3 Mile Island. This is located in close, about 10 miles from Harrisburg, Pennsylvania. And this is the worst accident in the United States. What happened is the fuel came really close to a complete meltdown, which again, if something happens to the coolant, the fuel rods get hotter and hotter and hotter and hotter. And if they get to a temperature where they can melt through the steel containment and then through the concrete and get released. So it came really close to melting. It melted through the steel containment chamber, and it was coming really close to melting through the concrete of the containment building. Okay, this example is actually used for both sides of the argument, should we or shouldn't we? Okay. This is a good example of why we should use nuclear power, and this is a good example of why we shouldn't use nuclear power. Because basically everything that could go wrong did go wrong. Okay, we have equipment errors, we have human errors, we have literally everything that could possibly go wrong. And the reactor was destroyed, completely destroyed. It was not reusable, but at the same time, radiation did not really get released and nobody was harmed. So everything that did go wrong could go wrong, but at the same time, we managed to contain all the radiation and nobody got hurt. So that's why it's a for it and against it. So this is basically what happened. I'm going to try really hard to explain what happened. But basically, there was a secondary line. And remember, the secondary line was pumping because this is a pressurized water reactor. So we have the pressure water and we have a secondary flow. Okay, well, somehow air got into this secondary line, and it caused the pumps to shut down. So that water was no longer pumping, which isn't a huge deal because we have backup generators, right? Well, the generators didn't kick on because earlier maintenance had been working on them and forgot to turn them back on. So human error number one, right? It was an equipment error to start off with. Human error number one, the backup generators were disabled, okay? Which again is not a huge idea because the people operating the machine should have seen, okay, my pump's not working, my generators didn't kick on, what's going on, right? But, oh yeah, there were these giant yellow tags in front of the warning light, so they didn't see them flashing going, the pump's not working. So there's human error again, right? So then,
Were they not trained to check?
well, think about the people who are working in power plants are probably not the ones with the college degrees. They're just trained to do their job. They probably don't understand the science behind it. You know, I mean, I'm sure they go through a lot of training, but they're still not the brains of the operation usually. They're not the ones that actually understand what's happening in the nuclear reaction. Because you guys, I mean, this is probably the first time this has really been explained to you.
Yeah.
Right? Okay. So, again, the backup pumps were not working correctly. So, oops.
So then, back to earlier, it says there's no possibility of it exploding, but they have some.
Well, it doesn't, it's not a chemical explosion like an atom bomb. It has a steam explosion, but that is not an atom bomb. That does not create the mushroom cloud. That does not create all the devastation. It still releases radiation, but it's definitely the lesser evil than an atom bomb, right? So anyhow, the pump is not working. Nobody saw the warning lights. This is happening. So the system began to overheat. So a pressure valve was then opened because this is pressurized water, right? So they then opened the pressure valve to kind of try to release some of the pressure to keep it from overheating. Well, when they opened the pressure valve, they had another equipment failure, and they tried to close it, and the computer said, yes, the valve is closed, but the valve was not closed. And so they thought they had fixed the problem. The pressure started going down, so all the readings were saying, okay, we've got this under control. And then shift change happened. Second shift left and went home to their family. Third shift came in. Okay? And so now third shift is walking into a nightmare, basically, because everything was supposed to have been under control, but that pressure valve is now open. So basically what's happening is the pressurized water is no longer working properly. So what's going to happen to the fuel rods? They're going to start heating up and heating up and heating up and heating up and heating up. So now this is starting to happen. And what happens as our pressurized water starts to get really, really, really hot? The decomposition of the water happens. What happens when water breaks down? Hydrogen gets created. What happens if there's a spark in hydrogen? Boom, it explodes. But luckily, there is no spark. Okay, so yes, the pressure valve was open, and yes, hydrogen gas was being created, but somebody finally started to get this under control. It took 8 days to get this under control. So yes, a teeny tiny bit of radiation was released when the valve was opened, but not enough. They technically weren't even evacuated, the surrounding area, because such a little amount of radiation was released that they decided that it wasn't harmful. They told pregnant women and children under 5 it'd probably be a good idea because their DNA is still changing, but it shouldn't have harmed normal people, and there hasn't been any documented radiation poisoning or anything like that. So everything that could go wrong did go wrong, right? But we were still able to contain it and nobody got hurt. So it's kind of like a good example. It took 30 days for the complete cool down, and now the reactor is done. This plant doesn't run anymore. After this accident, the government the ones that are running, they can keep running, but we're going to just kind of take a little break from it because that could have been really bad. All right, so that's example number 2. Example number 3 is Chernobyl. This was in 1986. Okay, this again occurred in the Soviet Union. Ukraine used to be part of the Soviet Union. I don't think it technically is anymore. And this site held 4 reactors. They used graphite moderator. However, this site had very poor safety, and this would have by no way been legal in the United States. Okay. This is what happened on the Chernobyl site. The workers did an experiment on reactor 4. They wanted to see what would happen if they turned off the safety features and powered up and ramped up the power. Okay?
Let's just see the stupidest thing.
Basically, this led to 2 explosions. The first explosion was a steam explosion because the steam is producing so much pressure. First one was a steam one, but then as our water is decomposing, it forms hydrogen. So then the second one was a hydrogen explosion, which is a chemical explosion, which is bad.
How long would it take for it to do that?
I don't know, it's in your reading somewhere. Okay, when the steam, probably with the steam explosion, it blew off the concrete lead of the containment. So immediately radiation starts releasing into the environment around it. And then we have the hydrogen explosion, which not only released radiation, but blew it really, 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 really far.
Like
Okay.
a mushroom cloud?
No. Okay, now that it has been exposed, the radioactivity was spewed into the atmosphere and it burned for 10 days. Okay, so all this radiation is just leaking out for 10 days. Okay? This accident released 200 times the radiation than Hiroshima and Nagasaki combined. 200 times the radiation levels. Okay? What they did, the majority of the people, the military was then sent in to try to contain all the radiation that they could and clean it up. The majority of the people who were involved in the cleanup died of radiation poisoning. And what they did is they buried this by 5,000 tons of boron, sodium carbonate, sand, clay, and lead. They use these because boron is a neutron absorber, right? So that's why it's trying to make the reaction stop. And then after they got it to the fire to go down and the reaction to stop, well, then we have all this radiation. Even if we were to clean it up, what in the world would we do with it? So they just covered the whole site in concrete. Kind of like a sarcophagus. Is that how you say that? Okay. Well, bad thing about their covering it in concrete is they didn't do a very good job about it. So the concrete is deteriorating. So it's breaking down. So if it breaks down too much, what's going to happen? All that radiation that they're trying to contain is releasing. So now they are trying to recover it to keep the radiation contained. All right, and this was an accident caused in Japan, and this is probably a good example of there was no equipment failures. There was no human error. This is just sheer bad luck. Okay, this happened in Japan in 2011. You guys remember that really big tsunami, that really big earthquake they had? This happened because they had a 19-foot retention wall for tsunamis, which in most, that's pretty good. That's going to be the majority because most earthquakes are under 7.5. Okay, so for the most part, they should have been fine. But this was a 9.0 earthquake, and the tsunami was 30 feet high. Okay, so the retention wall basically did nothing. So what's happened is, as soon as the earthquake happened, they shut the reactors down because it took the tsunami a good 45 minutes to an hour to get to landfall because the earthquake was off the shore. And so they shut the reactors down instantly, knowing that a tsunami was on its way, trying to give them as much time as possible to cool down, but you can't stop the reaction, right? They inserted all of the control rods that they could, so it was definitely slowing down, but it wasn't stopped. So then, what happened, do you think, when the tsunami hit? The electricity stopped because it's flooded. So the backup generators kick on. Well, most backup generators use gas. What do you think happened to the gas generators? They were flooded. Okay, so then that left battery generators. Well, the battery generators only had a life of 8 hours. So they worked for 8 hours to keep the reaction cool. But then, as the battery started to die, the water took a long time to recede, and so it just caused a radiation leak. But it was a 20-kilometer radius was contaminated with radiation. So this is probably the best example of no matter what you do, you can't control everything. They did everything that they could to try to stop the reaction. They did everything they could to control it, but life happens, right? All right. Good thing about this was most of the people were evacuated, so there weren't people around. There was things around, but most people, as soon as they saw the tsunami warning, they left. And so there weren't a lot of people around, so that's good news. All right, so we've been spending a lot of time on talking about fission. So now let's talk about fusion a little bit. Fusion is wonderful, okay? But it's hard to control. Fusion has several advantages. First of all, it produces more energy per pound of fuel. So we can produce a lot of energy with less reactants. This is why hydrogen bombs are more powerful than an atom bomb, because it produces more energy. Okay? Also, fuel is unlimited because the fuel is hydrogen. Hydrogen we can get from seawater. The deuterium and the tritium that we're talking about, we can produce from oceans. Well, the Earth is 70% ocean, so for the most part, we have an unlimited source of energy. Okay, well, it also produces fewer radioactive byproducts, so we have less waste. And the reactors are safer. If anything went wrong, then the temp would drop. Well, in order for fusion to happen, we have to be at really, really, really high temps. So if a tsunami were to hit this power plant and the electricity would die down, no more heat would be created. If there's no more heat, then there's no more fusion. So it's kind of like if something were to happen and the heat were to go away, the reaction would stop immediately. So it does kind of have a fail-safe. Well, sounds pretty good, doesn't it? So why don't we use it? Well, in order for us to do controlled fusion, we would have to not only generate but maintain 50 to 100 million degree temperatures. Okay. In a hydrogen bomb, we create these temperature by first using an atom bomb. So if you remember me talking about hydrogen bombs yesterday, we used fission to start the process. Fission created the temperatures necessary to fuse the hydrogen bombs. Okay, well, trying to get away from fission, right? We're trying to produce something a little bit stronger. So, at these, and not only that, but at these temperature, matter exists as a plasma, which is kind of like the fourth state of matter. Basically what happens, if you take a gas and you heat it up even more, it's kind of like you get a soup of cations, and there's no electrons. So things start to move a little bit more fluid. So it's almost like you go solid, liquid, gas, and then you kind of start to move a little bit more like a liquid again. Okay? Well, what about containment? How in the world would we contain something that is 100 million degrees? Okay, can you think of any products that wouldn't melt at 100 million degrees? How in the world would we contain this type of reaction? Well, there are two possible ways we could possibly contain this. The first one is magnetic confinement. The second one is inertial confinement. So let's talk about the first one. Magnetic confinement uses magnets. Basically, we are trying to trap the plasma between magnetic mirrors in a torus, and it is a donut-shaped chamber of some sort. Okay? If the plasma were to touch the outside of whatever container that we're using, it would instantly cause it to cool down. If the temperature cooled down, we would no longer be able to create fusion because we need to maintain those temperatures. So in this type of confinement, the magnetic field prevents the plasma from moving to the sidewalls. So it's trying to keep the plasma kind of flowing in a circle like a donut without touching the walls. Okay, in order for this to happen, we would need very strong electromagnets, and they would also need to be cooled to near absolute zero, which absolute zero is as cold as you can possibly get. We've actually never physically, technically gotten there before. Okay, currently, if we were to try to use this method, it would take so much energy to try to keep our plasma from touching the outside of our confinement that it would require more energy to maintain the reaction than the reaction would even produce. So it would be more expensive. It would cost more money to create the energy than the energy would be worth. So that's not going to work, right? Okay. The second type of confinement is inertial confinement. This is if I were to drop a frozen pellet of H2 or H3. These are the isotopes of hydrogen. If I were to drop a small frozen pellet onto the center of a reactor and heat it from absolute zero to fusion temperatures in a fraction of a second. To do this, what they do is it's kind of like they take lasers and they're going to pinpoint a whole bunch of energy into this pellet all at one time, and they're going to cause it to kind of like superheat. Okay, this is also going to take think about how much energy it would require. First of all, have a laser that could do that, and secondly, to go from absolute zero, which is negative 273 degrees Celsius, which I can't convert to Fahrenheit in my head, but it's a really, really low number, to millions of degrees in a fraction of a second. That almost strikes me as almost impossible. So, in theory, fusion would be good, but we can't quite figure out how to make it work efficiently. So if we could figure it out, it'd be good news, but we're not there yet. So why do we need nuclear energy? Well, we talked about electricity, we talked about power plants, we talked about all these things, but there are lots and lots and lots of other uses for nuclear energy. First of all, it's something called a tracer. Okay, tracers allow us to detect one molecule per 100 billion molecules. Okay, one example of why we would use this is if we have a waste site. So it doesn't necessarily have to be a nuclear waste site, it could just be a landfill. We want to know how fast the contamination is going to spread in our groundwater, right? Because we don't want the pollution from landfills getting into our water, correct? So how fast would this happen? What they could do is they could put a radioactive tracer at the landfill and then just find a well nearby and just continually check the well for that tracer. If it takes 2 weeks for the tracer to wind up in the well, then it takes 2 weeks for the pollution to travel that far. If the tracer never appears in the well, then that landfill is in a good spot. That means that there is no contamination of groundwater. This is also, they do this a lot in health. For instance, they will have you consume iodine, a radioactive version of iodine, and that goes straight to your thyroid. So if you have a thyroid issue, we would be able to detect that isotope of iodine in your thyroid because the rest of your body doesn't use it. That's how they do it in the health professions. Another use for nuclear energy is, again, a type of power source. Small reactors can be built for special applications. So initially, we have satellites. When we were first studying satellites, how can we power a satellite that is millions of miles away, orbiting the Earth, but at the same time we can't transport power back and forth to it? It's like we can run a electricity cable to it, right? But at the same time we need to be able to communicate with it. So what they would do, since we need such little amount of fuel, they put a little amount of, a little tiny uranium reactor on a satellite. It could power it for years and years and years and years and years. But the bad part about that is what happens to satellites sometimes? They fall out of orbit, and sometimes they come crashing back down to Earth. Well, if we have a tiny nuclear reactor in a satellite and it crashes, which has happened several times, what happens? Radiation is released. Okay? The Soviet Union, or Russia, it might have been Russia by this point, they made, I think, 31 nuclear energy satellites. I think 19 are still in orbit. The rest of them have fallen to Earth. So, another good way that we use nuclear energy is in pacemakers. Pacemakers allow a person's heart, people who have irregular heartbeats, it kind of gives them a little shock when their heart starts beating out of a weird pattern, correct? Well, it needs an energy source as well, but you don't want to walk around being plugged into a wall, correct? That's not practical. So it's almost like a tiny little battery that lives sometimes. I think there was 2 different sources that they talk about in your book, but one of them will last for 25 years. One of them will last for 88 years. So the chance of your pacemaker failing, if you're using this type of power source, would be slim to none, which is good, because if you have a pacemaker, you don't want it failing, correct? All right, a few more types that we do. Nuclear energy can also produce mutations, which is usually a bad thing, but sometimes it's a good thing. Ionizing radiation, which is, again, the radiation that transfers electrons back and forth really fast. This can alter the DNA of organisms, which can increase the rate of mutation, which usually is bad, but there are a few good applications for it. So these can also, sometimes this is what we're talking about when we're trying to do selective breeding into crops and animals. So if there's one crop that's doing better than others, we can selectively breed maybe that specific type of crop in order to get it to last longer or be fresher on the shelves for longer, so on and so forth. The part that you probably come into contact with most often is food preservation, which is actually given another name called irradiation. Basically, food is exposed to radiation when it comes off the field. So if we're talking about fruits, as they are picked while they're in the processing stage, they are exposed to irradiation before they even make it to the supermarket. And you can tell which foods have been that because usually there's a warning label on it telling you that it's been irradiated. And a lot of people are very against irradiated foods. But basically all that the irradiation does is it kills the microorganisms on the outside. So it's not like it becomes radioactive. It's not like it has radiation on it. It's exposed to radiation for a few seconds, kills all the microorganisms. If there's no microorganisms, the fruit or whatever stays fresher for longer. Therefore, people are going to want to buy it. It's going to last at your house longer, so on and so forth. It's kind of just like when we cook food, aren't we doing some sort of preserving it? If you back in the old days before they had refrigerators and freezers, they would salt food, right? There's lots of different ways to preserve it to kill the microorganisms. This is just the newest way. One thing people have with irradiation that could possibly be bad is if you're killing the microorganisms, if you're messing with their DNA, you could possibly be changing something in the food as well. But he had a good point in the book. He said, yeah, you might be changing something, but cooking changes the chemical composition too. Okay? So does salting things. Any type of preservation changes the chemical composition. So it's like, which is your bigger evil? Another use is to sterilize insects. Some insects cause great harm to livestock and other animals. So we need a way to get rid of them. But pesticides are bad because they contaminate the crops. They can make animals sick. They can make people sick. They're very toxic. So we don't want to use those. So we've had to kind of try to beat around the bush to kind of try to control our pests a little bit. So, for instance, I think they talked about a type of fly in the book. If they sterilize the male flies, they were competing with the fertile males. And so only half of the females were getting only half of the eggs were being fertilized. So then only half of the amount of maggots. So the next season, it just kind of started to drop. If half of them are being killed off every single year, after a few years, these types of insects are just wiped away from these parts, which I'm sure has some negative drawbacks. But again, you just kind of have to outweigh them. Which one's worse, killing all of your livestock and your plants or killing the insect itself? Again, lots and lots of things to consider. Nuclear medicine used in diagnosis and treatments. Some radioactive elements concentrate in specific types of tumors and cancers, making them easy to find and identify. I talked about iodine a little bit. Okay, it goes straight to your thyroid. They also use boron when you have a brain tumor, because boron is not radioactive. You don't want a radioactive isotope in your brain. But boron acts as a good moderator, so therefore it can pinpoint things a little bit easier. The bad thing about nuclear medicine, injecting yourself with chemotherapy or radiation, is it doesn't just signal the bad cells, does it? It goes for everything. So it kills the good cells along with the bad, which is why people get so sick, which is why their hair falls out and everything like that, because it's not just killing the bad cells. One that is most commonly used around us is radioactive dating. This is how we determine the age of organic materials. Organic materials are anything that is carbon, so this would be trees or animals, or this is what archaeologists do when they're digging and they find remains or trying to age them. This is how they use radioactive dating. Basically, carbon is in our atmosphere all the time. Okay, we have carbon dioxide in our atmosphere all the time, and there's probably been carbon dioxide in our atmosphere since the beginning of time. And they assume, because we don't know any better, that it's been about the same levels. Well, when you die or when an organism dies or organic material dies, it stops absorbing carbon dioxide from the air. So some of it is going to be carbon-14, some of it's going to be carbon-12. But if it stops absorbing carbon-14, that carbon-14, which is radioactive, continues to decay into carbon-12. So what they do is when they find something, they test to see how much carbon-14 is left. And then they can use a percentage, and they can figure out how old it is. And to figure out that they were right, they compared tree rings. A tree produces a ring every single year. So then they can compare the amount of carbon levels in artifacts to the number of tree rings, and then they can see that their math is correct or not. This is actually how they figured out that carbon dioxide levels have not been the same throughout time. It actually peaked about 2,000 years ago. It peaked, and so there was more carbon dioxide, so that means the carbon dating was a little bit faster. And so they've had to adjust their calculations just a little bit. But for the most part, it stays the same. And lots and lots of homework.
Oh, thank goodness we're done.
27 problems. All right, so before you guys all run out of here, let's go